Hello everyone, my name is Shixun Huang. I'm from MIT University. The topic of our paper is towards efficient motif-based graph partitioning and adaptive sampling approach. Motif refers to significant and frequent patterns in networks. These significant interaction patterns are essential elements and building blocks of various networks. The higher order organization formed by motif are fundamental for control and function of complex systems and provides deep insight on community in networks. For instance, we can base on motif M6 in the first figure to clearly reveal different species in the aquatic layer. Thus, how to preserve motif within the same community during clustering is very important, which is the research topic of this paper. Existing method on this research topic follow a two-step workflow, where the first step is to compute motif-based edge weight, where the weight equals to the number of isomorphic induced subgraph containing this target edge. And the second step is calling a graph partitioning kernel on the computed weighted graph. Below is an example motif-based weighted graph based on the input motif square. And the ideal partitioning result will keep the induced square subgraph in the same cluster. Existing methods suffer from efficiency bottleneck, as the first step needed to enumerate all isomorphic subgraphs. In this paper, we study minimizing motif-based weight of crossing edges. To avoid exactly subgraph enumeration, we propose two sampling approaches, SMGP and SMGP+. We proved that the solution quality of our proposed method is guaranteed, and our method can work with different graph partitioning kernel. Our methods are able to produce high quality solution compared with the one based on the exact edge weight. And our methods are highly efficient and can achieve up to 3 orders of magnitude speed up. The fundamental element of our sampling approaches is subgraph expansion, which consists of 3 steps. The basic idea is that we incrementally expand the sample subgraph starting from a randomly sampled edge until the size of the sample graph is equal to the input motif. Suppose the red edge is the sampled starting edge. We randomly choose label edge colored by blue and include the endpoint of the sampled edge together with its edge connected to the red part for the subgraph expansion. As the result, the size of the sample graph colored by red is increased, and we repeat this process until the size of the sample graph is equal to the input motif. After the subgraph expansion process, we use Horst-Thompson inverse probability weighting scheme to estimate the edge weight of the starting edges based on whether the sample graph is isomorphic to the current motif or not. We observe that SMGP requires an excessive number of samples to ensure that each edge has a small estimation error. However, not every single edge plays a critical role in affecting the partition quality, and the samples dedicated to those non-significant edges are largely wasted. To further improve efficiency, we propose SMGP+, which dynamically adjusts the sampling distribution of the starting edge to improve the partition quality while maintaining the same sample size. In SMGP+, we multiply the previous sampling probability of each edge by its partitioning factor and neighborhood factor. Where the neighborhood factor indicates the neighborhood density, we think that edges in the dense region tend to be contained in many isomorphic subgraphs. and the partition factor quantifies the importance of the edge on the solution quality. We introduce a concept called connection strength, which measures how easily the inaccurate weight estimation of edge incident to a specific node will change the placement of this node from the current partition to a different partition. Based on this concept, we compute partition factor of each node by considering all pairwise connection strength between the partition containing this node and a different partition. Suppose figure A is the optimal partitioning result with the smallest weight of crossing edges, where the ground truth edge weight is colored by red. Here, we only show a small part of the whole networks and focus on the placement of node B and the node edge. Suppose node B is the partitioning result of SMGP and SMGP plus with theta samples based on the uniform sampling distribution. From this figure, we can see that the placement of node B is more unstable than edge, since the difference between the total weight of edges connected to node B in the same partition and the one of crossing edges is much smaller than node edge. Thus, the inaccurate estimation on edges connected to node B will more easily influence the result. Thus, in the second iteration, SMGP will put more focus on estimating edges incident on node B than node edge. As the result, SMGP plus manages to produce a result with the smaller edge cut weight than SMGP. We propose a customized exponential function to compute the partition factor based on the intuition that a node with weaker connection strength should have higher partition factor. Due to the computation, we need to consider during the computation, we need to consider that the connection strength of an edge could be different based on which endpoint we are analyzing. For edges whose endpoints are in two different partitions, we prove that the difference between edge weight estimated by our method and the expected one will be bounded as the sample size increase. And we'll also prove the theoretical guarantee of our solution in terms of the partitioning quality. We use 7 graph patterns as the input motif for experiments. And these patterns are reported to be very significant and frequent patterns in real-world network across different disciplines. We conduct the experiment on 8 real-world social networks ranging from small scale to large scale and sparse one to dense one. We compare our method with the state-of-the-art exact motif counting method and test the robustness of our method with 2 popular partitioning kernels, where Fennel aims to maximize the modularity score and the MAPPR aims to minimize the conductance. This table is the statistics of EMGP, recording the running time and the count of each pattern in the corresponding networks. We terminated if you cannot finish within a month. As we can see, EMGP failed to compute the statistics on patterns of high frequency in large social networks, and it took more than 6 days to compute the result for pattern Q1 on dataset cast. Due to the time limit, we only show partial experiments on input patterns from Q1 to Q5, and we can have similar observation on other motif and datasets. These slides present the experimental result with Fennel as the partitioning kernel, where each row corresponds to the result on the same dataset. For each test, we sweep over different choices of sampling size in each iteration and choose the one which leads to the fastest convergence. As we can see, SMGP only performs well in some cases and it mostly fails to converge to a stable performance even after 20 iterations. On the other hand, SMGP Plus converges much faster than SMGP with promising result. These slides present the experimental result with MAPPR as the partition kernel, and we have the similar observation. And here we present the running time comparison between EMGP and the convergence time of SMGP Plus. And SMGP Plus can achieve up to 3 orders of magnitude speed up. During the experiment, we observed that the performance across different motifs on the same dataset could be different. We suspect that this observation is influenced by the different size and the distribution of motif instances. For example, if the motif click of size 4 have more instances than other motif of size 4 in the graph, then it will be easier to sample the click of the size 4 than other motif of the same size. That's all. Thank you.